Have you ever wondered what really happens when two galaxies meet? Not a firework show of crashing stars, but a quiet pull that reshapes everything. Gravity stretches disks into long tidal tails. Gas clouds compress, new stars ignite, and central black holes find more to eat. From far away, it looks slow. Up close, it's a set of linked steps: distort, trigger, merge, settle. The night sky keeps its calm, while orbits trade momentum and structure changes hands. That's the puzzle we'll unpack. Why most stars never collide, why gas does, and how a merger can both build and quench future starlight. If clear, steady exploration is your pace, a like and subscribe helps others find it. Settle in, and let's trace the physics of a meeting that remakes a galaxy. What truly happens when galaxies collide is slower and quieter than the word collision suggests. The timescale stretches across hundreds of millions of years, sometimes more. Two large systems draw together under gravity, pass, pull, and fold into each other, changing shape step by step. A galaxy is not a single object, but a mix of stars, gas, dust, and an unseen mass called dark matter. None of these parts sit still. They orbit, compress, heat, cool, and form new structures as the encounter unfolds. The result is not a single crash, but a long sequence of tides and responses. Over time, the pair becomes one. To follow this process, it helps to see what a galaxy is. Think of a vast collection of stars arranged in a disk, a sphere, or something less tidy, all bound by gravity. Gas flows through this structure and sometimes collapses into new stars. Dust blocks and scatters light and helps cool gas. Around all of it lies a much larger halo of dark matter that we do not see directly but measure through its pull. This halo holds the galaxy together and sets the stage for how it moves and how it will merge. Galaxies come in several main forms shaped by their past. Spiral galaxies are disks with arms. The arms are not rigid. They are regions where matter is a bit denser, so gas turns into stars more often there. The light is bluer because many of those new stars are hot and short-lived. Some spirals show a bar of stars across the center, guiding gas inward and feeding central activity. Elliptical galaxies look smoother. They hold older stars on more random orbits and have little cool gas for new star formation. Many of the most massive galaxies are ellipticals, likely built by earlier mergers that heated and mixed their stars. Irregular galaxies do not fit clean shapes. Many have been disturbed by neighbors, stretched by tides, or jolted by bursts of star formation after an encounter. Across all types, size varies. Giants can hold trillions of stars. Dwarfs may have only a few billion, yet they are the most common and often travel as companions to larger systems. Our own Milky Way is a barred spiral with a disk about 100,000 light-years across. It holds a few 100 billion stars, many with planets. At the center sits a supermassive black hole, a compact object whose gravity is strong enough that not even light can escape once inside its boundary. The galaxy rotates as a whole, but not like a solid wheel. Stars in the inner regions complete orbits faster than stars in the outer disk, and orbits tilt and wobble above and below the mid-plane. Beyond the visible starry disk lies the dark matter halo, hundreds of thousands of light-years in radius. This halo contains most of the galaxy's mass. Without it, the Milky Way's outer stars would orbit too fast to remain bound. The disk would fly apart. Gravity is the planner behind all of this. At everyday scales, it keeps your feet on the floor. In space, it shapes orbits. Newton's laws show how masses attract. Einstein's general relativity explains this attraction as the bending of space and time by mass and energy. For the flow of galaxies across billions of light years, both views produce the same practical guidance. Mass causes curvature. Curvature guides motion. Gravity pulls matter into clumps, makes gas crash into itself, and lets stars and planets form. It also sets up the tides that act during close encounters, stretching one side of a galaxy more than the other, drawing out long streams of stars called tidal tails. Dark matter deepens the potential wells that gravity carves. Though we cannot see dark matter, we infer it from rotation speeds, from the motion of galaxies in clusters, and from the way massive objects bend light, a phenomenon called gravitational lensing. Across the universe, about 5 times more matter is dark than ordinary. Ordinary matter is made of atoms. Dark matter is not. It does not shine or absorb. It interacts mostly through gravity. In a merger, the halos of dark matter from both galaxies pass through each other with little direct friction, yet their combined gravity helps trap the visible parts and guide the final shape of the remnant. The large-scale map of the universe reflects this partnership between gravity and dark matter. Galaxies collect along filaments of dark matter, forming a cosmic web with great knots where many filaments meet. Between filaments lie large voids with few galaxies. A galaxy's path is not random. It follows this landscape. Over time, gravity pulls neighbors together along the filaments. Groups become clusters. Pairs become single larger galaxies. Collisions are not accidents. They are the natural flow of mass down the slopes of the cosmic web. Why do galaxies move in the first place? The early universe was not perfectly smooth. Tiny differences in density gave some regions a small head start. Those regions pulled in more matter and grew. As material fell inward, it did not fall straight. Small twists in the flow gave forming galaxies spin. Nearby structures tugged on them and added drift. Today, the Milky Way and the Andromeda Galaxy are closing in on each other at about 250,000 miles per hour. The first close pass is expected in roughly 4 billion years. That number is large to us, but modest on galactic timescales. Long before that, we see motion in other ways. Satellite dwarfs swirl around the Milky Way. The large and small Magellanic clouds move through our outer halo, and streams of stars mark past mergers, already absorbed. When two galaxies approach, the first signs of an interaction show up in their outskirts. Tides lift stars from the edges and form bridges between the pair. Gas in the disks feels gravity and also collides with other gas. It compresses, shocks, and cools. This often triggers bursts of star formation. Massive young stars appear, light up nebulae, and soon explode as supernovae, stirring the gas again. The central black holes may respond as well. As gravity torques the disks, gas loses angular momentum and moves inward. Some of it feeds the central black holes, which can then shine as active galactic nuclei. Over time, dynamical friction, the drag that comes from moving through a sea of stars and dark matter, slows the cores. The two centers spiral toward each other, complete close passes, and eventually coalesce. Despite the word collision, stars almost never hit stars. The distances between them are too large. What changes during a merger are the orbits. Stars are flung into new paths by the shared gravity of the pair. Gas clouds do hit and compress. Dust lanes twist. The combined system settles into a new form over a long time. Depending on the mass ratio, gas content, and relative angles, the final galaxy may look like a smooth elliptical, a regrown spiral with a thickened disk, or a disturbed system that takes longer to calm. The details depend on many parameters, but the outline is consistent. Tides first, inflows second, coalescence last, relaxation after. History shows how we learn to read these signs. For a long time, astronomers argued over whether the faint smudges in the sky were clouds within the Milky Way or distant island universes. In the early 1900s, measurements of variable stars in the Andromeda Nebula revealed it was far outside our own galaxy. That result expanded the known universe and opened the door to the study of galaxy types, distances, and motions. With better telescopes on the ground and in space, we began to see bridges, tails, rings, and shells, the debris of encounters. We now observe merging pairs at many stages and compare them with computer simulations that follow gravity, gas dynamics, and star formation. The slow choreography becomes clear when seen in large samples. Dark matter leaves marks in these events as well. In some systems, the stars and gas separate slightly during a clash, because gas experiences friction and stars do not. The dark matter follows the stars, not the gas. Mapping this offset helps measure how much unseen mass is present and whether dark matter interacts with itself. So far, it appears to be mostly collisionless, meaning it passes through other dark matter without much drag. That property shapes how quickly the merged halo settles and how the visible parts gather inside it. The pace of a merger depends on mass and geometry. Two large, gas-rich spirals meeting face-on can trigger an intense burst of star formation and then wind down into an elliptical-like system with older stars and little cool gas left. A large galaxy absorbing a much smaller dwarf, called a minor merger, heats and thickens the disk but does not erase it. Repeated minor mergers can build a stellar halo around a disk and leave faint streams as evidence. Encounters that do not quite merge can still matter. A close pass can warp a disk, tilt a bar, or drive gas inward, changing the rate of star formation for a time. Not every change is violent. Many disks regrow. After a gas-rich merger, fresh gas can cool from the halo and settle into a new rotating disk. Over a few billion years, spiral structure can reappear, especially if the combined system keeps receiving cold gas from its surroundings. Bars can form later and move material inward again. The picture is not a single path, but a set of branches controlled by mass, gas supply, and environment. Speaking of environment, galaxies rarely live alone. Small groups like our local group contain a few large galaxies and many dwarfs. Larger clusters hold hundreds to thousands of galaxies embedded in a hot, thin gas called the intracluster medium. In clusters, galaxies move fast and feel strong tides. Gas can be stripped from them as they plow through the hot medium, a process called ram pressure stripping. Stripped galaxies may stop forming stars and fade to red. In groups, speeds are lower, so mergers are more common. Over time, many cluster ellipticals are thought to be the product of earlier group mergers that were later drawn into the cluster. At the centers of massive galaxies, supermassive black holes also merge. As the two galaxy cores close in, their central black holes form a binary. Stars passing near the binary carry away energy, bringing the pair closer. Eventually, Gravitational waves, ripples in space-time, carry enough energy away that the black holes combine. The final black hole may recoil slightly from the asymmetric wave burst, then settle at the center. Mergers like this should be common over cosmic history. Future observatories sensitive to long-period gravitational waves aim to measure these events directly and link them to the visible signs of galactic mergers we already see. From the human view, these changes are slow, but they add up. Star formation rises and falls. Gas moves inward or is blown outward by supernovae and black hole activity. Some galaxies shut down and stop making new stars for a time. Others restart when fresh gas arrives. Across billions of years, the mix of galaxy types shifts. In the early universe, more galaxies were clumpy and forming stars rapidly. Later, more became smooth and quiet. Collisions and close passes help drive that shift by moving gas around and building mass in the centers. The numbers involved are large, yet the rules are few. Gravity sets the pull. Dark matter deepens the wells. Gas physics sets how material cools, collapses, and forms stars. Feedback from stars and black holes heats and stirs the gas, sometimes halting star formation, sometimes just slowing it. When two galaxies meet, these same rules run in a different configuration. Tides add energy to orbits. Torques move angular momentum. Shocks compress gas. The system then tries to find a new balance. It rarely returns to the old one. It is natural to ask what happens to planetary systems in all of this. Most stars do not collide, so most planetary systems remain bound to their host stars. The main risks are long-term changes in the star's orbit within the galaxy, and rare close passes of other stars that could perturb outer comet clouds. For planets like Earth, the danger from a galaxy merger is small compared with local stellar evolution. The Sun's future brightness and its own life cycle matter more than the shape of the Milky Way's disk. Still, on very long timescales, the changing gravitational field of a merging galaxy can stir outer reservoirs of comets and asteroids. These effects are statistical and unfold over tens to hundreds of millions of years. The path ahead for our region is known in outline. The Milky Way and Andromeda will draw closer, pass through each other, and merge. The Triangulum galaxy, a smaller neighbor, may take part as well. The first passage will pull out long tidal tails. Star formation will rise in some regions and drop in others as gas is heated and moved. After several passes, the cores will combine. The remnant may look more like a rounded system than a thin spiral. Over more time, gas will settle or escape, and the new galaxy will calm. The Sun, by then older and brighter, will still orbit the combined center if it is not lost to a new path. The night sky for future observers, if any remain to see it, would show a different pattern of stars, but the physical laws would be the same. Looking back, our view of galaxies has progressed from faint smudges to detailed portraits. We now count star clusters, map gas flows, and trace dark matter through gravitational lensing. We also simulate entire mergers with millions to billions of particles, then compare those runs with systems caught at different stages in the sky. The match is never perfect, and that helps. Every mismatch points to physics we're missing or measurements we should refine. The goal isn't a single pretty picture, but a tested account of how two galaxies become one. To ground that account, we wind the clock backward to the conditions that set the whole story in motion. After the Big Bang, about 13.8 billion years ago, the universe was hot, dense, and expanding. Most matter was hydrogen and helium, spread almost evenly, with tiny ripples in density. Gravity amplified those ripples. Slightly denser spots pulled in more material, grew heavier, and pulled in more again. From these seeds rose the first clumps of stars and the first small galaxies. The initial conditions, our observations and simulations now track forward, linking early fluctuations to the complex structures we measure today. Early galaxies were compact and irregular. Their shapes looked unsettled because they were still assembling. Gas was plentiful, so star formation was intense. Their light skewed blue and bright because most stars were young and massive. These systems lacked the clean structure of modern spirals or the smooth profiles of giant ellipticals, but they held the raw material for growth. As the universe aged, galaxies changed through internal cycles and through contact with neighbors. Inside each galaxy, stars formed from cold gas, lived for times set by their mass, and died. Supernovae and stellar winds returned heavier elements, carbon, oxygen, iron, to the gas. That enrichment allowed dust to form and helped gas cool more easily, which improved the efficiency of making the next generation of stars. Over many cycles, a galaxy's average color shifted from youthful blue toward warmer tones as the share of short-lived hot stars fell and older populations dominated. The same process made rocky planets possible around some stars because heavy elements are needed to build them. Outside, influences mattered too. In the early universe, galaxies were closer together, so encounters were common. Interactions did not happen in minutes. They stretched across hundreds of millions of years. When two galaxies drew near, their stars mostly missed direct contact because the spaces between stars are enormous compared with stellar sizes. Even so, the combined gravity field reshaped both systems. Tides pulled out long streams, disks warped, gas clouds collided and compressed, raising the rate of star formation. Two galaxies could eventually bind and merge, producing a larger remnant. Collisions were not only disruptive, they were also constructive. Hierarchical growth, small to large, by repeated mergers built today's massive galaxies. The biggest ellipticals in cluster centers likely formed through many such unions. Their smooth, rounded appearance reflects stars stirred onto random orbits by past mergers. Our Milky Way shows evidence of this process as well. Faint stellar streams in the halo trace former dwarf galaxies pulled apart and absorbed. Future events lie ahead. The Milky Way is on track to meet Andromeda and possibly Triangulum, continuing the same growth pattern on a grander scale. Across billions of years, a galaxy's life can swing between active and quiet phases. A spiral rich in cold gas can form stars steadily. Later, gas may be used up, heated, or stripped, slowing new star formation. The system reddens and becomes quiescent. Repeated mergers can thicken and smooth the disk, reducing visible structure until the galaxy resembles a rounded elliptical. Most stars then are older and fainter, still glowing but spending their fuel slowly. The galaxy remains large and luminous, yet its activity level drops. The times involved are far beyond human experience. A single pass in a galaxy encounter can span hundreds of millions of years. A full merger can take around 1 billion years or more. For comparison, recorded human history is only a few thousand years long, and the dinosaurs reigned for hundreds of millions of years. Against galactic time, even that long chapter is a brief episode. Galaxies evolve on patient schedules. Species and civilizations can rise and fall without visible change in the host galaxy over a single lifetime. Patience does not mean fragility. Galaxies are resilient collectives. They can be stretched, stirred, or fed without falling apart. The Milky Way's halo holds streams that reveal earlier meals. Each new accretion adds stars, gas, and momentum, altering structure in subtle ways. Some galaxies follow relatively quiet paths, far from heavy traffic. Others live in crowded regions where interactions are common and evolution runs faster. The mix of shapes we observe today, spiral, elliptical, irregular, records those different journeys. This wide view can shift personal perspective. Human schedules run on days and years. Galaxies move through chapters that last billions of years. Rather than making human concerns smaller, the contrast adds context. The universe has room for fast and slow stories. Light from a distant galaxy takes millions of years to reach us. What we see is a record of older stages. While we observe, the galaxy continues its own changes, most of which unfold too slowly for one generation to track directly. In that sense, a galaxy is more than a collection of stars. It is a timeline written in light. The phrase "galaxies colliding" invites images of violent crashes. Reality is quieter. The key fact is spacing. Even in dense regions of a galaxy, the distance between stars is so large that direct star-star impacts are extraordinarily rare. A useful mental check is scale. If a star were the size of a grain of sand, the next grain might be miles away. When two galaxies overlap, their stars pass like distant travelers. What actually changes are the orbits and the gas. Tidal gravity stretches the outer parts and can fling material into long arcs called tidal tails. Gas behaves differently from stars because gas clouds are big enough to collide and can radiate away energy. When gas compresses, it often forms stars, producing bright starburst regions. Massive young stars light up nearby clouds, then end as supernovae that stir and enrich the gas again. Collisions, therefore, tend to increase the birth of new stars rather than destroy old ones. Orbits of stars respond to the shifting gravitational field. Some stars are placed on wider, longer paths around the merged center. Others move inward. A small fraction can be tossed into the outer halo or, in rare cases, gain enough speed to escape entirely. For any potential observers on a planet around a distant star, the changes would be undetectable within a lifetime. Constellations would alter only across immense stretches of time. Equal mass mergers often erase spiral structure and create a rounder, smoother remnant that we classify as an elliptical. The stars end up on orbits with many directions, so the disk signature fades. When a large galaxy absorbs a much smaller companion, a minor merger, the disk survives but thickens. The smaller system is stretched out and added as streams and shells. Observations reveal such features around many galaxies, including ours. Gas physics is central in these events. Unlike stars, gas clouds collide head-on. Shocks form and drain energy from the gas, allowing it to sink toward the center. Inflows can feed the supermassive black holes in galactic cores. When enough material enters the region near a black hole, it can ignite an active galactic nucleus, AGN. The disk of infalling matter heats and shines, sometimes outshining the rest of the galaxy. In extreme cases, we see a quasar, a very luminous AGN visible across cosmic distances. Thus, mergers can wake quiet black holes and briefly make galaxies extraordinarily bright. None of this happens quickly. A typical merger unfolds in stages. First approach, tidal disturbance, passage, separation. A second approach, deeper interlock, and final coalescence, followed by a long relaxation. Each stage can take tens to hundreds of millions of years. Compared with biological evolution on Earth, that is a timescale where simple life can become complex, while two galaxies complete a single major encounter. Astronomers piece together this sequence by observing many systems at different stages and by running computer simulations. The antennae galaxies show long, symmetric tails that mark a recent major pass. The Whirlpool galaxy exhibits a grand spiral pattern, enhanced by a small companion tugging on its disk. Other examples show bridges, rings, or shells. Simulations built with gravity and fluid equations reproduce these shapes and let us test how mass ratio, gas content, and encounter angle change the outcome. Dark matter plays a quiet but decisive role. Each galaxy sits in a large, extended dark matter halo. During a collision, the halos interpenetrate and overlap. Because dark matter does not collide like gas, it passes through with little friction, but its combined gravity sets the potential in which stars and gas move. In some special systems, we can see stars and gas offset from each other after a clash, while the mass traced by gravity lies with the stars. These cases help confirm that dark matter is mostly collisionless, shaping how mergers settle and how fast the remnant relaxes. Environment modifies the script. In rich clusters, galaxies move fast through hot, thin gas. Ram pressure stripping can peel gas from disks, shutting down star formation even without a direct merger. In smaller groups like our local group, relative speeds are lower, so mergers are more likely. Over cosmic time, many present-day cluster ellipticals were assembled in groups and later collected into clusters. The internal history of a merged galaxy can still be complex after the main event. Fresh gas may cool from the halo and rebuild a rotating disk over a few billion years. Spiral patterns can reappear. A bar can form and drive more gas inward. Star formation can restart at a lower rate. Alternatively, strong feedback from an AGN or repeated hot outflows can keep gas from cooling, leaving the system quiet. Which path a galaxy follows depends on mass, gas supply, and surrounding conditions. Planetary systems are usually safe through all of this. Most stars keep their planets because direct stellar collisions are rare and because the changes to orbits occur gradually. Outer comet clouds may be perturbed statistically, raising or lowering the chance of long-period comets over vast time windows. For Earth, the Sun's evolution is the dominant factor long before any merger with Andromeda is complete. Observations across many wavelengths reveal different layers of these processes. Ultraviolet light highlights young, massive stars in recently triggered regions. Visible light shows the bulk of the stellar population and the geometry of tails and bridges. Infrared reveals dust warmed by star formation and the flow of cooler gas. Radio observations trace neutral hydrogen, stretching far beyond the bright optical disks, mapping the raw fuel for future stars. X-ray data exposes hot gas from shocks and from central black hole activity. Putting these views together yields a consistent picture. Interactions drive inflows and star formation. Halos set the framework. Feedback regulates the pace. The patterns created by encounters are distinctive. Tidal tails are long, thin structures of stars and gas, drawn from the outskirts by differential gravity. Some tails curve back and fall into the remnant. Others remain faint arcs for a long time, slowly dispersing. Bridges are strands of material, connecting two galaxies during or after a close pass. They form when gravitational pulls from both systems raise tides in the same region and draw matter across the gap. Stellar streams mark the remains of smaller companions pulled apart along their orbits. Around the Milky Way, multiple streams thread the halo, evidence of ongoing assembly. At a larger scale, all of this sits within the cosmic web. Galaxies gather along dark matter filaments and move toward dense nodes. The web guides where encounters happen and how often. Over time, mass flows from low-density regions into higher-density ones. Groups grow, merge into clusters, and evolve. The same physics, gravity, gas dynamics, feedback runs at every step, from the first clumps after recombination to the complex structures we map today. When two similar mass disks merge, the final shape depends on orbital geometry and gas fraction. A gas-rich merger can light up with starbursts, feed the central black holes, and then fade as gas is heated or exhausted. The stellar remnant is often pressure-supported and rounder. In gas-poor mergers, there is less new star formation, and the system settles faster into a smooth elliptical. In minor mergers, the main disk thickens but can survive, while faint shells and ripples record where the infalling system looped and dissolved. The Milky Way provides a local laboratory for these ideas. Dwarf galaxies such as Sagittarius are being tidally disrupted, leaving star streams that wrap around the halo. The large and small Magellanic Clouds interact with each other and with the Milky Way's halo, drawing out a long ribbon of neutral hydrogen called the Magellanic Stream. These nearby signatures show that assembly is still underway in our own neighborhood and give us concrete structures to explain and predict. To turn those traces into a tested picture, astronomers run computer models that replay full encounters from start to finish. On modern clusters, N-body simulations represent stars, gas parcels, and dark matter, with particles tied together by gravity, while the gas also obeys fluid physics, cools, forms stars, and is heated by supernovae, or black hole activity. Set two model galaxies on crossing paths, and the familiar patterns emerge. Disks twist, tails unfurl, bridges connect the pair. The match to real images is not perfect, but it is close enough to probe causes, rank which processes matter most, and interpret the streams and clouds we see around the Milky Way. These runs compress billions of years into minutes. They show a steady sequence. First approach raises tides. The first pass throws out long streams and often lights up star formation. After drifting apart, the pair falls back for a deeper pass. Dynamical friction drag from moving through a sea of stars and dark matter slows the cause. The centers spiral inward, the galaxies coalesce, and the messy remnant relaxes. Change one input, and the outcome shifts. A higher gas fraction gives stronger starbursts. A more equal mass ratio tends to erase disks. A different angle of approach alters where tails and bridges form. Simulations are useful because they make clear what drives the shapes we see. Tidal forces rearrange stellar orbits. Gas clouds collide and lose energy, so they sink inward and form stars. Feedback from young stars and black holes then heats and stirs the gas, sometimes shutting down further star formation for a while. Dark matter halos overlap and guide the whole process because they contain most of the mass and set the gravity field in which the visible parts move. Observations across many wavelengths check each step. Ultraviolet light traces very young, hot stars formed in recent bursts. Visible light shows the bulk of the stars and the overall geometry. Infrared reveals warm dust in star-forming regions and the flow of cooler gas. Radio maps neutral hydrogen stretched far beyond bright stellar disks. X-rays show shock-heated gas and activity near growing black holes, when a simulated merger predicts a tail full of young clusters. Astronomers look for UV bright knots and gas at matching locations. If a model says inflowing gas should feed the center, observers search for warm dust, compact radio sources, or X-ray emission. Agreement builds confidence. Mismatches point to missing physics or wrong inputs. The pace remains slow in physical time, but the patterns are regular. Orbits redistribute, disks tilt and thicken. Rings and shells can appear after near head-on passes. Some stars are placed on wide loops that form a faint halo. A small number can escape with high speed and become unbound. Most stars remain within the merged system, but on paths that bear little memory of the original neat spiral orbits. Antennae galaxies, often called a merger, in mid-act, are a clear case. Two spiral disks have passed closely and thrown out long tidal tails. Along those tails, gas has been compressed into clumps that host young star clusters. The central regions glow where gas has flowed inward and star formation has spiked. Simulations set up with two gas-rich disks, an almost prograde encounter, and a small initial offset reproduce the twin tails and the bright overlap region. Most models predict that after a few more passes and the final coalescence, the remnant will look rounder and smoother, with less clear spiral structure. That end state fits the view that many large ellipticals were built by past gas-rich mergers. The Cartwheel Galaxy shows a different path. A smaller intruder passed nearly straight through a larger disk. The impact drove a circular density wave outward through the disk, like a moving ring of compression. Gas in the wave collapsed into new stars, making a bright outer ring. Spoke-like features trace where material is being pulled inward and where instabilities connect the ring and inner disk. Simple models where a compact companion crosses a disk can reproduce a clean expanding ring, the bright edge, and the delay between the passage and the peak of star formation in the ring. The system highlights how a fast, central passage can reorganize a disk into a ring without a long, repeated dance. The Whirlpool Galaxy, M51, illustrates a milder but still powerful interaction. It is a nearly face-on spiral with a smaller companion, NGC 5195, tugging on its outer arms. The pull sharpens and exaggerates the spiral pattern and triggers star formation along the arms. Ultraviolet and H-alpha maps show strings of young clusters. Infrared and radio maps reveal dust lanes and gas feeding those regions. Simulations with a lower mass companion that passes just outside the main disk yield arm kinks and asymmetries close to what is observed. The system shows that a full merger is not required to reshape a spiral and raise its star-forming rate. A close pass can do both. All three systems demonstrate the same set of drivers acting in different settings. Tides act on stars. Collisions and shocks act on gas. Dark matter defines the deep potential well. Feedback can either allow new stars to keep forming or, if strong enough, heat and expel gas, lowering the rate. The visible forms, tails, bridges, rings, thickened disks, are the footprints of these processes. Their lifetimes differ. Tails fade as stars spread out and surface brightness drops. Bridges break as the pair separates or coalesces. Rings expand and dim as the wave moves outward and the new stars age. Art words are not needed to explain why these shapes look pleasing. They are simply the direct result of gravity and motion working over large scales. Long arcs trace where orbits were stretched most. Smooth curves mark regions where many stars share similar paths. Radial spokes in a ring reflect where the disk supports instabilities after a central punch. The geometry is a record, not a design. Simulations are not perfect movies. They rely on resolution limits and subgrid rules to capture complex gas behavior below the size a model can track directly. Star formation, black hole feeding, and stellar feedback are parameterized with simple laws tuned to match a broad set of data. That said, the tests are strict. A good run must reproduce not only one picture, but also the range of structures and ages seen across many systems, the gas fractions, the rates of star formation, and the timescales implied by stellar populations. When multiple independent runs with different codes converge on similar outcomes for the same initial setup, confidence rises that the main physics is correct. A key insight from both data and models is how sensitive outcomes are to initial conditions. Mass ratio is crucial. Major mergers, similar masses, tend to erase ordered rotation and build rounder pressure-supported systems. Minor mergers, large with small, thicken disks and feed stellar halos, but often leave the main disk intact. Gas fraction sets how intense any starburst will be and how much of a disk can regrow later. Orbit geometry, prograde or retrograde, inclined or coplanar controls tail length and the symmetry of bridges. Encounter speed and environment matter too. Fast flybys in clusters often strip gas without merging, while slow approaches in small groups more easily end in coalescence. Dark matter's role is clearest when gas and stars separate slightly after a pass. Gas feels drag, stars do not. Where we can map mass from motions or lensing, the main mass peak follows the stars, not the slowed gas. Simulations that treat dark matter as collisionless reproduce that offset and the later settling of the combined halo. If dark matter interacted strongly with itself, the patterns would differ. Current observations tend to support the collisionless picture, which is the basis of most large-scale and merger models. Feedback marks another pivot point. When gas falls inward during a merger, the central black holes can switch on. An active galactic nucleus, AGN, forms when matter spirals into a supermassive black hole and heats up, releasing light and sometimes fast outflows. Those outflows can clear or heat central gas and reduce star formation for a period. Simulations include simple versions of this process to prevent too many stars from forming too fast. The balance is delicate. Too little feedback and the remnant becomes unrealistically bright. Too much and no disk can regrow. Observations of outflows, central cavities, and temperature maps help set the allowed range. Not all merger marks are bright. Some of the most telling features are extremely faint. Low surface brightness streams, shells, and plumes that surround galaxies at large radii. Deep imaging surveys reach these levels and frequently reveal signs of past accretion. Simulations predict similar webs of faint debris after both major and minor mergers. Matching the frequency and brightness of this debris between data and models is an active test of how often mergers happened and how long their marks persist. The time dimension is central. Tails are strongest soon after a close pass. Rings brighten as the compression wave sweeps outward, then fade. Bridges are most obvious near pericenter, when the cores are closest. After the final coalescence, kinematic signatures, how stars move, carry the history even when morphology looks calm. Observers read those motions by measuring line-of-sight velocities and dispersions across a galaxy, and compare them to simulated remnants at different ages to infer how long it has been since the last major encounter. Putting these threads together gives a simple working map. If you see two long, symmetric tails and a bright, clumpy overlap, you likely have a recent major pass in a gas-rich pair. If you see a strong ring with spokes, a near head-on encounter is favored. If a grand design spiral shows one arm stronger than the other and a small neighbor nearby, a tidal tug without full merger is a good bet. If a smooth, round system shows shells and ripples at low surface brightness, a past minor merger is the likely cause. Each case fits within the same physics, adjusted for mass, gas, and geometry. The value of this map is practical. It lets astronomers use a snapshot to reconstruct a timeline and to estimate how much gas moved, how many stars formed, and whether the central black holes were likely fed. It also guides future observations, where to look for shocked gas, where to search for young clusters, and how deep to image to find the faintest debris. The same logic feeds back into better simulations. By setting concrete targets a model must meet to be credible. These well-studied systems, antennae, cartwheel, whirlpool, serve as benchmarks. They pin down merger stages, show where star formation switches on, and set the balance between order and disturbance. As sharper images and deeper maps arrive, and as computing power grows, models can be tuned against these targets with tighter limits. The aim is not spectacle. It is a tested account of how gravity, gas, and dark matter turn two galaxies into one, and how to read those marks in the light we capture. With that framework in place, the next step is the engine at the very center that often responds most strongly when galaxies interact. At the centers of most large galaxies sits a supermassive black hole. Its mass can be millions or billions of suns, yet the zone it dominates can be smaller than our solar system. We do not see the black hole itself. We see its effects. Stars near the core move at very high speeds. Infalling gas heats up and glows. In active phases, that light can outshine the entire galaxy. Compact as it is, the black hole reaches far through feedback, winds, radiation, and sometimes jets, acting as a deep anchor that shapes a sprawling system. There is a tight link between a galaxy's central bulge of stars and the mass of its black hole. Bigger bulge, bigger black hole. This pattern suggests coevolution. As galaxies grow, they feed their black holes. As black holes flare and blow out energy, they change the gas supply that makes future stars. When galaxies collide, this partnership is stressed and often strengthened. Picture two galaxies on track to meet, each with a black hole at its core. As tides pull on the disks, gas flows inward. Over millions of years, the galaxies overlap more deeply and their centers draw near. The black holes are carried along, first wandering through the merged system, then settling into the shared center as a wide pair. At that point, they orbit each other as a binary. The orbit is large at first, but it shrinks over time as the pair gives energy to nearby stars and gas, and later, to space-time itself. Gravitational waves carry away the last energy. These are ripples in space-time, predicted by general relativity. You can think of them as tiny stretches and squeezes that pass through everything, too small to feel in daily life. As the black holes spiral inward, the waves grow stronger and faster. In the final moments, the pair whirls around at a significant fraction of the speed of light and merges into a single, larger black hole. For a brief instant, the power released in gravitational waves exceeds the combined light of all visible stars, but it leaves almost no light. The signal, is in the waves. Catching those waves took extraordinary care. In 2015, the LIGO observatories measured the first clear signal from two stellar mass black holes merging more than 1 billion light-years away. The change in length they detected was smaller than a proton's width, over kilometers of laser path. Since then, many more events have been recorded. Most star mergers of black holes or neutron stars are few to a few dozen times the mass of the Sunday. Each detection is a new way to study gravity and compact objects, not with light, but with the motion of space-time itself. Supermassive black hole pairs radiate at lower frequencies than ground-based detectors can hear. For these giants, space-based detectors will be needed. A mission like LISA is designed to track the slow, deep signals of massive binaries, tightening their orbits over months or years. Those measurements will help map how often galaxies merge, how fast their cores settle, and how black holes grow across cosmic time. These events are grand, but they are distant and slow. Even during a future Milky Way Andromeda merger, Earth will not be threatened by the central black holes. The timescale to bring the cores together is far longer than human history. The Sun's own life cycle matters more for habitability than any central merger. When the black holes finally combine, the effect will be dramatic on the scale of the new galaxy's core. Not in our local space. The role of a supermassive black hole is not only to consume, it also shapes. When gas falls inward, the region near the black hole can become an active galactic nucleus. Light and fast outflows from the core can heat or remove gas in the inner galaxy, reducing future star formation for a time. In other cases, gentle feedback may stir, but not clear the gas, allowing new stars to keep forming. The black hole and the galaxy respond to each other, a push and pull that helps set the pace of growth. From the point of view of a single star far from the center, a galaxy merger feels uneventful. Space inside a galaxy is mostly empty. The average distance between stars is so large that direct collisions are extremely rare. A simple scale helps. If the Sun were a marble, the nearest star would be another marble hundreds of kilometers away. Two overlapping galaxies can pass through each other, and almost every star still misses every other star. What changes our orbits? A star that used to travel on a near circle around the old center may be placed on a longer, tilted path around the new one. Some stars are pulled outward into long arcs that become part of a tidal tail. Others are nudged inward. These shifts happen slowly over millions of years, like a very gradual rerouting of traffic through a city. The star itself does not feel a jolt. It keeps shining as before, guided by gravity. Planetary systems are also stable in most cases. A star's grip on its planets is strong compared with the weak tides from distant passing stars. Earth orbits at about 93 million miles, and the Sun's pull at that range is the dominant force. Rare, very close stellar encounters can disturb outer comet clouds and, in unusual cases, could eject a planet, but the odds are small. For the vast majority of worlds, a galaxy merger is a quiet background change rather than a direct threat. Some stars do take on new roles. Those pulled into long tails can spend billions of years in the outer halo of the remnant, tracing wide, slow loops. Others join streams that wrap around the galaxy. These features are faint but common and help astronomers reconstruct past encounters. In all cases, the stars remain intact. Their cores continue fusion. Their light stays steady until fuel runs low. The Sun, for example, is about halfway through a roughly 10 billion year main main sequence lifetime. It will keep shining through any large-scale reshaping of the Milky Way. Young stars, by contrast, often owe their birth to the interaction itself. Gas clouds are large enough to collide. When they do, shocks compress them. Cooling then lets gravity take over. Dense cores form and collapse into star clusters. The hottest and most massive new stars burn bright and blue and live short lives. They soon explode as supernovae, returning heavy elements to the gas and stirring the surroundings. This cycle, compression, star formation, feedback, can be very active during and after a close pass. These processes are not abstract. We can trace them in many bands of light. Ultraviolet images light up recent starbirth. Infrared reveals warm dust that wraps young clusters. Radio maps show neutral hydrogen stretched into tails and bridges. X-ray data marks hot gas and energetic cores. Each band adds a layer to the same picture. The merger drives gas to new places, changes the pressure and density, and sparks fresh formation. Supermassive black holes, meanwhile, follow their own path to the center. As the merged galaxy settles, the two black holes lose energy to surrounding stars, a process called dynamical friction. If enough stars interact with the pair, the separation shrinks. Later, gravitational waves take over. If the binary is fed by gas, a circumbinary disk can speed the loss of angular momentum and help the merger along. When the final coalescence happens, the remnant black hole may recoil slightly from the asymmetric wave emission, then sink back to the center. The energy from an active core can alter the gas on large scales. Powerful outflows can clear central regions and halt star formation for a time. Gentler winds can keep gas warm and suppress the fastest collapse, leading to slower, longer-lasting star formation. In either mode, the black hole helps set the balance between new stars and quiet phases. Observations of outflow speeds, shock fronts, and cavities in hot gas give direct evidence for this feedback. For an individual star far from the center, even a bright active nucleus is simply a distant lighthouse. Light arrives after tens of thousands of years of travel. Winds and jets fade with distance. The star continues as before, while the galaxy's gas supply adjusts and the central engine cycles on and off. All of these changes rely on the same raw material, the cold gas and dust between the stars. Molecular clouds, giant chilly regions made mostly of hydrogen, are the nurseries of new suns. They are dark in visible light, but glow in specific radio lines and in the infrared. Collisions and close passes move, pile, and shear these clouds. Gravity then gathers the densest parts into cores. The details depend on turbulence, magnetic fields, and the local radiation field, but the outline is simple. More compression leads to more stars, up to the point where feedback pushes back. The fuels that form stars also feed black holes. During an encounter, torques remove angular momentum from gas and let it flow inward. Some of that gas settles into the central 100 or 1,000 light years and forms stars there. Some falls deeper and forms a disk around the black hole. Whether the outcome is a strong central starburst, a bright active nucleus, or both depends on how much gas is available and how fast it can move. As time passes after a merger, the high contrast marks fade. Tails spread out, bridges break, rings expand and dim. What remains are the kinematics, the motions of stars, and the makeup of the stellar population. These are long-lived clues. They let astronomers estimate when the last major event happened and how intense it was. They also explain why today's massive ellipticals are full of older stars and why many disks show thickened structures and faint streams. Seen this way, supermassive black holes sit inside a larger chain. They anchor the centers, set conditions nearby, and, when they finally coalesce, mark the deepest stage of an encounter. Stars most of the visible mass carry the long memory of orbits and past tides. Gas and dust, though dim to our eyes, set the near-term pace because they build the next generation. These reservoirs fill, move, and drain under gravity and feedback, becoming the raw material for new stars and, in time, new planets. To see how that link works in practice, follow what happens to the cold gas and dust when two galaxies draw close. When galaxies meet, cold gas and dust do not stay idle. Tides and shocks compress clouds, raise their density, and trigger wide fields of star formation. Interstellar gas is mostly hydrogen with a trace of helium and heavier elements. Dust grains, tiny bits of carbon, silicon, and oxygen scatter and absorb light, set temperatures, shield molecules, and mark where collapse can begin. With this mix in place, a passing encounter can switch quiet regions into active nurseries. Without it, a galaxy would simply fade as its old stars age. Compression is the key. A large cloud that was stable can be pushed over the line when pressure rises. Gravity then wins. The cloud breaks into clumps. Dense cores collapse further and become protostars. When a core gets hot and dense enough, hydrogen fusion starts, and a star is born. In a collision, many clouds feel this push at once, so many clusters appear together. Astronomers call the surge a starburst. During a burst, a galaxy can form new stars tens or hundreds of times faster than in calm periods. The signs are plain in many wavelengths. Young, massive stars emit strong ultraviolet light that ionizes nearby hydrogen. That gas glows in pinkish-red emission lines. Infrared images show warm dust around newborn clusters. Radio maps reveal long streams of neutral hydrogen stretching between partners, marking the raw fuel supply. X-rays trace hot gas, where shocks and supernovae heat the surroundings. Put together, the picture is a chain. Tides compress, gas collapses, stars ignite, feedback follows. Feedback matters because it shapes what happens next. Massive young stars blow winds, and some end their lives as supernovae after only a few million years. Both processes stir and heat the gas. Part of the gas cools and continues forming stars. Part is pushed away or kept warm and cannot collapse. Near the center, gas funneled inward can feed the supermassive black hole. If the core becomes active, outflows and radiation can limit further star formation in the inner regions. The result is a rise and fall pattern. Fast growth, then a pause or slowdown. Starbursts do not last long in cosmic terms. They use fuel quickly. In a few 100 million years, much of the easy-to-collapse gas is either turned into stars or heated and dispersed. The rate falls back toward normal. The galaxy that remains is different. It often has a larger central bulge, older average starlight, and less cold gas. Some disks rebuild later if fresh gas cools from the halo. Others settle into quieter shapes, with little new star formation. Nebulae are the visible parts of this cycle. Bright emission nebulae glow around young clusters where ultraviolet light excites hydrogen and oxygen. Reflection nebulae scatter blue light off dust near newborn stars. Dark nebulae are cold, dusty lanes that block starlight and mark dense regions where stars may soon form. In interacting systems, these nebulae are shifted, compressed, and sometimes drawn out along tidal tails. Their colors and brightness change with the local radiation field and chemistry, giving observers a way to map conditions across the system. The scale can be very large. A single massive star-forming complex can span hundreds of light years and contain thousands of infant stars. Some newborns will resemble the Sun and live for billions of years. The most massive will be brighter, bluer, and short-lived, ending in supernovae that add heavy elements to the surrounding gas. Those elements, carbon, oxygen, silicon, iron, are needed to build rocky planets, and eventually, biology. Collisions speed up this enrichment by creating many massive stars at once. Gravity also directs where stars form. During a close pass, torques remove angular momentum from gas in the disks and drive it inward. That raises central densities and supports a core starburst. At the same time, outer gas can be pulled into bridges and tails where other pockets collapse. The result is a patchwork: bright knots near the center, glowing beads along arcs, and extended radio-bright filaments of hydrogen. Each patch shows a slightly different clock phase in the same chain of events. The burst phase ends, but the merger continues. Tidal tails fade as stars spread out and surface brightness drops. Bridges thin and may fall back. The two cores perform more close passes and finally coalesce. The rotation that once kept thin spiral arms coherent is mixed into more random motions. The combined system usually looks rounder and smoother. We call it an elliptical when the disk signature is gone and the stars fill a spheroidal volume. The physics behind the shape change is simple to state. A collision adds energy and scrambles orbits. In a spiral, stars share a common direction and speed. After a major merger, stars move on many tilted paths with different speeds and phases. That mixed motion does not support a thin disk, so arms vanish. If the gas supply is low or removed, there is no new disk to rebuild spiral structure. The light becomes dominated by older, cooler stars, which is why ellipticals look redder. Gas loss and heating are the other half of the transformation. Starbursts and active nuclei drive winds. Clustered supernovae carve holes and push gas outward. Some gas escapes the shallow parts of the potential well. Some remains hot in the halo and takes a long time to cool. With less cold gas available, star formation slows or stops. The galaxy looks calm, not because the stars are still, but because the fuel for new stars is scarce. In dense environments like clusters, extra processes help. Galaxies move through hot intra-cluster gas and feel ram pressure that can strip their own gas, especially from the outskirts. Fast flybys shake stars, but rarely lead to mergers. Over time, the mix of effects past mergers, gas stripping, and heating builds large, smooth ellipticals that dominate cluster centers. These central galaxies can contain trillions of stars and sit in deep wells of dark matter. They often host very massive black holes whose past activity left cavities and ripples in the hot cluster gas. Calm does not mean nothing changes. Stars in ellipticals still evolve. Red giants blow off envelopes. White dwarfs cool. Neutron stars and stellar mass black holes remain from earlier massive stars. Globular clusters orbit in the outer regions. The central black hole may flare if a small galaxy or gas cloud ventures too near, but the overall structure is steady compared with the earlier, more eventful stages. The quiet phase can last for billions of years. The galaxy slowly fades as its stars age, Without new hot blue stars to boost the ultraviolet and blue light, the color shifts to warmer tones. Surface brightness drops as stars move outward. The most striking marks of the old collision tails and bridges disappear from easy view. What remains are subtle signatures, faint shells, weak ripples, and the pattern of stellar motions. Astronomers read those signs to reconstruct when the merger happened and how violent it was. Across many systems, a consistent pattern emerges. Encounters stir gas and build stars. Feedback heats and limits further growth. Orbits randomize, and morphology shifts. If gas later cools and accretes, a new disk can form, and some spiral structure can return. If not, the remnant stays smooth and red. The path taken depends on mass, gas fraction, orbit geometry, and environment, but the key steps repeat. This framework explains why the most massive galaxies in cluster cores are usually smooth and old, why many disks show thickened components and faint streams, and why strong starbursts are often linked to interactions. It also connects the growth of central black holes to the broader galaxy. Gas driven inward by tides can feed the black hole. Energy released near the core can then alter the gas supply, closing a feedback loop that ties black hole mass to bulge mass. From the ground and from space, instruments now track these phases with more detail. Deep imaging reaches the low surface brightness outskirts, where streams and shells reside. Integral field spectrographs measure the motion of stars and gas across a galaxy, revealing rotation, dispersion, and hidden substructures. Millimeter arrays map cold molecular gas, the immediate fuel for stars. X-ray telescopes map hot halos and record signatures of past outflows. The agreement between these data and modern simulations strengthens the overall picture while highlighting places where models must improve. The same physics extends to smaller scales. Dwarf galaxies interacting with a larger host can trigger localized star formation and leave behind thin streams. In turn, the larger galaxy's gravity shapes those streams into loops and fans. Even within a single disk, smaller cloud-cloud collisions can start local bursts. Collisions across scales share the same ingredients: gravity to gather, pressure and shocks to compress, cooling to collapse, and feedback to regulate. When the gas reservoir is large at the time of a major merger, the starburst can be intense. When the reservoir is modest, the burst is weaker and the remnant settles faster. If fresh gas later arrives from the surroundings, star formation can resume at a lower rate. Bars can form and drive more gas inward, building central components and perhaps feeding the nucleus again. Over time, the system cycles through active and quiet periods set by supply and loss. In clusters, the balance tips toward quiet. Ram pressure and the hot intra-cluster medium keep gas from cooling easily. Many cluster galaxies show little recent star formation. In groups in the field, gas remains easier to accrete, and disks can be rebuilt. That is why environment is a strong predictor of galaxy type. Dense regions tend to host more smooth, red systems. Lower density regions host more disks with ongoing star formation. The long settling after a collision is guided by gravity's patience. Random motions average out. The merged dark matter halo stabilizes. The central potential becomes smooth. Minor mergers continue to add stars to the outskirts and keep halos growing, but they rarely change the inner shape once a large remnant is in place. The galaxy's future then looks like slow aging rather than sudden change. Through all of this, the core message remains practical. Gas and dust are the active medium. Interactions compress that medium and raise the star formation rate. Feedback regulates the burst and helps decide the remnant's fate. Randomized stellar motions and reduced fuel shift disks toward rounder, quieter forms unless new gas arrives to rebuild order. The visible arcs and colors are surface signs of these steps, and their timelines can be read from the light we receive. Look toward Andromeda, and you see a faint blur, easy to miss with the unaided eye. That blur is a full spiral galaxy much like the Milky Way, home to hundreds of billions of stars, and it is approaching our galaxy on a long, steady path. The distance is about 2.5 million light-years, so the motion feels slow, even though Andromeda moves toward us at roughly 110 kilometers per second. The encounter is not soon, in any human sense. The first close pass is expected in about 4 billion years. Long after Earth's continents shift, the sun brightens, and our species either changes or vanishes. The important point is that the meeting is real and already underway. As Andromeda closes in, its size in our sky would grow over many millions of years. A pale oval would become a bright disk. The two galaxies would pass through each other's outskirts and then their inner regions. Stars are very far apart, so direct impacts are extremely unlikely. What changes are orbits and gas. Tidal forces pull out long streams of stars. Gas clouds collide and compress, and new star-forming regions turn on. The first passage throws out tails and bridges. Gravity then brings the pair back for another pass. After several such loops, the cores settle together, and the system relaxes into a single, larger galaxy that will likely be rounder and smoother than a thin spiral. Our solar system is expected to survive the merger, in the basic sense that the Sun will keep its planets, while the larger structure shifts around it. The Sun's path may widen, tighten, or tilt. It could end up in the remnant's inner regions or in a long tidal stream. The main risks to any given planetary system remain rare, close stellar flybys and long-term changes in comet clouds. Both are low-probability events. The bigger influence on Earth's habitability is the Sun's own evolution, not the merger itself. The sky during the approach would change slowly. Over thousands of generations, the faint patch of Andromeda would brighten and develop visible structure. A careful observer could notice changes over many lifetimes, not over days or years. Constellations would shift as stars move on altered orbits. If star formation is triggered, bright nebulae would appear in new places. None of this would look like a sudden explosion. It would be a drawn-out transformation, measured in millions of years. This future encounter is not unusual. Galaxies are part of a large-scale network of matter. They move along filaments of dark matter, gather in groups, and sometimes merge. Elliptical galaxies in cluster centers are strong evidence of many past mergers. The Milky Way is no exception. Its halo holds streams from smaller galaxies that have already been torn apart. The local group Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and many dwarfs, is a bound system, and its largest members are on intersecting paths. Simulations make the picture clearer. Astronomers build models that include stars, gas, and dark matter, then set initial positions and velocities based on measurements. The code follows gravity for all components, gas physics for cooling and pressure, and simple rules for when gas forms stars and when supernovae or central black holes heat the surroundings. In these models, the Milky Way and Andromeda do not collide once and stop. They swing by, recoil, and return, with long tidal tails marking each encounter. Over several billion years, the pair settles into a single remnant, changing the input-mass ratio, gas content, or angles changes details like tail length or where star formation peaks, but the overall path approach passes, coalescence, relaxation remains. One key result is that most stars remain intact. The distance between stars is so large that direct collisions are rare even when the galaxies fully overlap. The main effect is a new distribution of orbital energy and direction. Some stars are placed on wider orbits and become part of a faint halo. Others move inward. A small number get enough speed to escape entirely. For observers inside the system, the night sky would slowly reorganize, but stellar lifetimes and fusion in their cores would continue as usual. Dark matter sets the deepest part of the gravitational well and makes the merger certain. The Milky Way and Andromeda each sit inside halos far larger than their visible disks. These halos interpenetrate first. Their combined pull keeps drawing the visible parts back together after each pass until the cores merge. Without this invisible mass, the two galaxies could have missed or separated more easily. With it, the outcome is a single, larger galaxy. Companions will join the story. The large and small Magellanic Clouds are already interacting with the Milky Way's outer halo. The Triangulum Galaxy may pass through the system during the merger, adding its mass and gas. Many faint dwarfs will be stretched into streams or absorbed. The final remnant will contain stars from all contributors. Its outer regions will keep low surface brightness traces of past accretion for a long time. Naming the remnant is a playful detail, but the physical picture is serious. An end state like Milk-Dromada is expected to be a large, roughly elliptical system with a central black hole more massive than either present one. The thin disks and well-defined spiral arms would be gone because random motions would dominate over ordered rotation. If the final halo still holds enough cool gas, a new disk could regrow over time. If not, the system would remain smooth and red, making few new stars. The timeline matters. The first clear tidal features could appear soon after the first close pass. Star formation would rise in places where gas is compressed near the center and along tails and bridges. Later, as gas is used or heated, the rate would drop. The final coalescence of the cores would add another burst of inflow and, possibly, central activity if gas reaches the black holes. After the merger, the system would calm and the bright, short-lived stars would fade, leaving an older population that sets a warmer overall color. For Earth, the sun's brightening is a larger near-term issue than the merger. Over the next 1 to 2 billion years, increased solar output is expected to raise temperatures and reduce surface water. That timescale overlaps the early approach but precedes the main stages of the collision. Whether Earth is still habitable when Andromeda dominates the sky depends on climate and life's adaptability, not on tidal forces from the merger. The steady pull that reshapes galaxies acts too slowly and too weakly at our location to cause sudden local change. Simulations let us test these claims. They predict the timing of tail formation, the location of starbursts, and the structure of the remnant stellar motions. Observations of other merging pairs, some with long symmetric tails, some with ring features, some with one strong spiral arm and a visible companion, match the patterns. This agreement gives confidence that the same physics governs our future. The models also highlight the parts that remain uncertain, such as the exact transverse motion of Andromeda and the gas fraction available at the time of closest approach. Improved measurements continue to sharpen those inputs. The role of central black holes adds another layer. Each galaxy hosts a supermassive black hole. During the merger, gas can lose angular momentum and flow inward, feeding the cores and turning on active galactic nuclei. Outflows from these active phases can heat or remove gas, shaping how quickly star formation declines. Later, the two black holes orbit as a binary and, after much longer times, merge and emit gravitational waves. That final step does not change stars far away, but it anchors the remnant center with a larger, single black hole. The local group as a whole will change shape as mass collects in the remnant. Dwarf galaxies will continue to feed the outer halo. The combined dark matter halo will deepen. Over very long timescales, the system will appear as a single, dominant galaxy, with a wide halo of streams and faint shells. Its stars will age and redden. If cold gas continues to arrive slowly from the surroundings, low-level star formation could continue in small pockets. If not, the system will fade gently as its stars evolve. Practical numbers help keep the scale clear. The current distance to Andromeda is a few million light-years. The closing speed is a small fraction of the speed of light. The first close pass occurs in billions of years, not millions. The duration of a full merger is also billions of years. A human lifetime is far too short to notice more than subtle changes in the positions of a few nearby stars. The merger is large, certain, and slow. The lesson extends beyond our local future. Galaxy interactions are a common path to growth. They build large ellipticals in clusters. They thicken disks and seed halos. They trigger star formation and feed central black holes. They also leave clear marks that can be read with deep imaging and careful measurements of stellar motions. Our own system provides a chance to link a detailed prediction to a well-observed example once the process is underway. Simulations do not provide a script with every detail fixed. They provide a framework that explains the main features and defines which measurements matter most. For the Milky Way Andromeda case, the framework says, approach along the dark matter filament, first pass with strong tides, repeated encounters, coalescence, and a likely smooth remnant. Stars mostly avoid collisions. Gas drives the bright phases and then runs low. Black holes follow the centers and merge much later. Companions contribute streams and mass to the outskirts. The outcome is a stable, larger galaxy consistent with what we see across the universe in systems that have already completed similar journeys. In the early universe, collisions were routine. The cosmos was smaller and denser, so young galaxies sat closer together. They were not grand spirals or smooth ellipticals yet. They were small, clumpy, and rich in cold gas, forming stars at a fast pace. Short distances and high gas content made encounters frequent. Telescopes that look far back in time, meaning far away, often find irregular, warped systems. Those shapes are not mistakes. They are signs of growth, galaxies merging, gas compressing, and stars turning on in bursts. When gas-rich dwarfs ran into each other, clouds crashed and squeezed, pressure rose, gravity won, and many stars formed at once. Astronomers call these events starbursts. They produced bright, short-lived, massive stars that ended as supernova after only a few million years. Each burst stirred and heated the surrounding gas, then spread heavy elements, carbon, oxygen, silicon, iron, back into space. Over many cycles of merging and starbirth, small fragments assembled into larger, more ordered galaxies. This steady building is often called galactic assembly. Like towns growing into cities, little systems combine to make the large disks and spheroids we see today. no present-day galaxy is truly pristine. If you could read the fossil record in their stars, you would find traces of past meals, streams from torn dwarfs, thickened disks from minor mergers, and halos filled with debris. The Milky Way's outer regions carry these marks. Stars in different streams show distinct chemical fingerprints because each small galaxy had its own pattern of element production. By comparing those fingerprints ratios of elements like magnesium to iron, astronomers reconstruct a family tree and count many earlier mergers already folded into our spiral. Collisions did more than build size. They shaped types. After a merger, gas that remains can cool and settle into a rotating disk. Over time, density waves in that disk make spiral arms, where gas forms stars more often. In more violent, gas-poor mergers, ordered rotation gets scrambled. Stars end up on orbits pointing many directions, and the remnant becomes rounder and smoother, what we call an elliptical. In this way, gravity and gas physics turned early chaos into the variety of forms seen now. Heavy elements also spread because of these encounters. The first stars formed almost entirely from hydrogen and helium. Heavier elements appeared later, forged in stars and released in winds and supernovae. Collisions triggered many massive stars at once, speeding that enrichment. The result was gas, with enough metals, astronomy's term for all elements heavier than helium, to form dust grains and rocky planets. Without frequent interactions to spark starbursts, the universe would have stayed poorer in the ingredients needed for solid worlds, and, eventually, biology. Collisions fed central black holes, too. Most large galaxies host a supermassive black hole in the middle. These objects did not start huge. They likely began as seeds from the deaths of very massive stars, or from direct collapse of dense gas. During an encounter, torques remove angular momentum from gas and send it inward. That inflow can feed the black hole, making an active galactic nucleus that shines across the spectrum and sometimes launches powerful outflows. Repeated fueling episodes let central black holes grow to millions or billions of solar masses. When two galaxies merge, their black holes can form a binary and, after a long time, coalesce events that send gravitational waves through space. Modern detectors have already heard waves from smaller black holes. Future instruments are planned to catch the low-frequency signals from the supermassive kind. Evidence for a collision-rich past is widespread. Deep images show pairs with faint bridges and long tails. Closer galaxies display shells, ripples, and streams at very low surface brightness, tidal debris left by minor mergers. The Andromeda Galaxy shows loops and shells around its disk. The Milky Way's halo hosts arcs like the Sagittarius Stream, clear proof of dwarfs being stretched and absorbed. These structures are the fossils of growth. Rates changed with time. In the dense early universe, encounters came often, on timescales of hundreds of millions of years. As space expanded and galaxies grew, average distances increased and direct collisions became less frequent. Yet gravity still binds neighbors into groups, so mergers continue, just more slowly. The local group itself is headed toward a major union in the far future, demonstrating that this process has not ended. Under the large-scale drama lies the steady life of individual stars. A star's behavior is set by a simple balance. Gravity pulls inward, fusion pushes outward. Stars form when cold hydrogen gas in a molecular cloud collapses and heats until fusion begins in the core. During the main sequence phase, hydrogen fuses into helium at a stable rate. The Sun has been on the main sequence for about 4.6 billion years and should remain there for roughly another 5. Many stars spend the vast majority of their lives in this calm state, providing steady light and heat to any planets in orbit. As core hydrogen runs low, the balance shifts. In Sun-like stars, the core contracts and heats. The outer layers expand and cool. The star becomes a red giant, larger, more luminous, and redder. In this stage, a star can engulf inner planets. Mass loss increases as gentle winds carry material away. Eventually, outer layers drift into space and become a planetary nebula, a glowing shell lit by the hot central remnant. Despite the name, planetary nebulae are not planets. Early observers simply saw round shapes in small telescopes. The glow fades over tens of thousands of years as the gas disperses. In the center remains a white dwarf, a compact object about Earth-sized, but with a mass around that of the Sunday. It no longer fuses. It shines from leftover heat and cools slowly over billions of years. The universe is not old enough for any to have cooled to true darkness, so no black dwarfs yet exist. White dwarfs mark the quiet end for stars up to about 8 times the Sun's mass. More massive stars live fast and end violently. They burn hotter, fuse heavier elements in their cores in a series of stages, and reach the limit where fusion can no longer support the core. Collapse follows. The outer layers rebound and explode as a core collapse supernova, releasing a burst of light and neutrinos and driving shocks into the surrounding medium. For a short time, such an explosion can outshine an entire galaxy. The expanding debris carries heavy elements into space, enriching the interstellar gas for future stars and planets. The collapsed core becomes either a neutron star or a black hole, depending on mass. A neutron star is only about 20 kilometers across, but holds more mass than the Sunday. Matter inside is so compressed that protons and electrons combine to form neutrons. Some neutron stars spin rapidly and beam radio or X-ray light from their magnetic poles. We detect them as pulsars. If the original star was very massive, collapse continues past the neutron star stage, and a stellar mass black hole forms an object with gravity so strong that nothing, not even light, can escape once inside its event horizon. Galactic collisions affect where and how often these endpoints appear, without changing the basic rules. By compressing gas, encounters create more massive stars for a time, so supernova rates rise. The added heavy elements help dust form and cool gas, which then shapes the next generation of stars. Feedback from supernovae and from active black holes can blow bubbles, drive winds, and sometimes shut down star formation locally for a while. Over longer spans, gravity and cooling bring gas back, and the cycle continues. Seen together, these layers assembly of galaxies, enrichment of gas, growth of black holes, and the life cycles of stars form one story. Early, crowded times favored frequent mergers and rapid star formation. Heavy elements spread, disks settled or were scrambled into spheroids, and central black holes grew with their hosts. Later, as space opened up, growth slowed, but the same physics still operates wherever galaxies meet. The large shapes we map across the sky are the sum of many past encounters. The light from each star tells us which stage it has reached. The gas and dust between stars reveal what the next stage may be. Collisions set the pace, but stars keep the beat through the steady rules of fusion and gravity. Stars set their own pace. Their lifetimes are fixed mainly by mass and internal structure, not by the large-scale events around them. In galaxy collisions, stars remain so far apart that direct impacts are essentially zero. The same fusion physics runs on inside each star. What changes is where new stars appear and how many are born. When galaxies merge, tidal forces and cloud-cloud encounters compress cold gas, dense regions collapse, and new clusters light up. Those newborn stars then follow the usual path. Long main sequence phases for low-mass stars, short and bright lives for the most massive, and the familiar endpoints, white dwarfs, neutron stars, or black holes set by initial mass. Over billions of years, the cycle links collisions to stellar evolution. Many of the stars now visible likely formed in periods of heightened activity triggered by past encounters. Some of those massive stars will end as supernovae, spreading heavy elements into the surrounding gas. Others will cool into white dwarfs and add to the diffuse glow of galactic halos. The larger point is continuity. Galaxies can live for tens of billions of years, but individual stars come and go on shorter clocks. Their deaths are not waste. The expelled material mixes back into the interstellar medium and becomes the feedstock for future stars and planets. In that sense, a merger is less a destructive event than a reset that increases the rate of star formation, setting many individual stellar lives in motion at once. This recycling is practical, not poetic. The carbon in organic molecules, the oxygen in air, the iron in cores of rocky planets, all are products of stellar interiors and supernovae. Some of those explosions likely occurred in galaxies that were being reshaped by collisions long ago. The universe does not discard raw material. It moves it between phases. A cloud collapses into stars. Stars enrich gas. Enriched gas cools more efficiently and forms the next generation. Collisions act as a trigger by gathering and compressing gas that might otherwise remain diffuse for much longer. As observers turned better instruments on interacting systems, one conclusion became unavoidable. Visible matter is not the full story. Gravity in these events points to an additional component that does not emit or absorb light. This component is dark matter. We infer it from motions, from the way galaxies rotate, and from how massive structures bend light from more distant sources. In collisions, dark matter's role becomes especially clear because it behaves differently from gas. A classic example is the Bullet Cluster, the aftermath of two galaxy clusters colliding at high speed. Clusters contain hundreds of galaxies. They also contain a large reservoir of very hot, thin gas that shines in X-rays and carries more mass than all the stars. During the impact, these gas clouds hit, slow down, and pile up between the clusters. If most mass were in that visible gas, the overall mass map would coincide with the X-ray glow. It does not. Using gravitational lensing, measuring how background galaxies are distorted by the cluster's gravity, astronomers mapped where the mass actually sits. The lensing peaks line up with the galaxies that have already moved past each other, not with the stalled gas in between. The conclusion is straightforward. Most of the mass passed through without strong collisions. That mass is dark matter, which interacts very weakly with itself and with normal matter, aside from gravity. This separation of mass and gas is hard to explain without dark matter. Collisions like the Bullet Cluster tell us another property. Dark matter appears nearly collisionless. When normal gas collides and heats, dark matter halos overlap and keep going. That behavior lets galaxies remain bound during encounters and helps determine the final shape after a merger. It also explains why spiral galaxies can rotate as fast as they do without flying apart. The extra gravity of the halo holds the disk together. Other systems, such as Able 520 and similar train wreck clusters, show more complex patterns that continue to test models. In a few cases, the inferred mass distribution is puzzling, which pushes theory to consider a range of dark matter properties and to improve lensing maps and gas physics in simulations. Across many systems, however, the broad picture remains consistent. Most of the matter is dark. It sits in extended halos around galaxies and clusters, and it interacts mainly through gravity. Current candidates for the particle nature of dark matter include WIMPs, weakly interacting massive particles, and lighter particles, such as axions. Direct detection experiments and astrophysical tests are narrowing the possibilities, but no confirmed particle has been identified yet. In mergers, the dark halo is the stage and the guide. Galaxies are embedded in halos much larger than their visible parts. These halos interpenetrate first. Their gravity keeps the partners bound after each pass, and the combined halo shapes the potential in which stars and gas settle. Tails, bridges, and shells form within this framework. The final remnant, often an elliptical, relaxes inside the merged halo. Without the halo, many encounters would not lead to a bound union. At the same time, another central actor responds strongly to mergers: the supermassive black hole, SMBH, in each galaxy's core. In quiet phases, an SMBH can be underfed. Gas and dust orbit at large radii, and little material reaches the inner parsecs. A collision changes the flow. Gravitational torques remove angular momentum from gas and drive it inward. Near the center, gas forms an accretion disk around the black hole. Friction in the disk heats the gas to high temperatures, and the disk radiates from radio up to X-ray energies. When the feeding rate is high, the galaxy hosts an active galactic nucleus, AGN. In its most luminous state, we see a quasar, bright enough to outshine the rest of the host galaxy. AGN are not only lights, they also drive winds, and in some cases, jets. Jets are narrow streams of energetic particles launched along magnetic field lines that are twisted by the rotating disk and the black hole's spin. They can extend thousands of light years or more, depositing energy far from the center. Outflows and jets can heat or remove gas from the central regions, reducing the ability of that gas to collapse into new stars. This feedback helps explain observed links between black hole mass and the mass or velocity dispersion of the galactic bulge. In short, growth of the galaxy and growth of the SMBH are connected. During a merger, the two SMBHs first wander within the combined galaxy, then find each other as dynamical friction slows them. They form a wide binary and, over time, shrink their orbit. Stars that pass nearby can carry energy away. If gas is present, a circumbinary disk can remove angular momentum. In the last stage, the pair loses energy through gravitational waves and merges into a single, more massive SMBH. The emitted waves are low frequency, best measured by planned space-based detectors sensitive to months-long or years-long cycles. When such signals are detected, they will provide direct timelines for how galactic cores settle after mergers. Mergers do not always create the same central outcome. Gas-rich encounters feed both starbursts and SMBHs and can leave a core with signs of recent activity and a large bulge. Gas-poor mergers build mass without much new star formation and settle faster into smooth systems. Bars that form later can again drive gas inward, leading to smaller central episodes. The details depend on gas fraction, mass ratio, and orbit geometry, but the mechanisms torques, inflows, accretion, and feedback repeat. Putting these threads together yields a practical view of what collisions do. They alter where stars are born by compressing gas. They enrich the gas faster by raising the rate of massive star formation and supernovae. They assemble mass by adding stars to halos and bulges. They reshape kinematics from ordered rotation to more random motions when the encounter is strong. They feed central black holes and, through feedback, adjust the future supply of cold gas. All of this happens inside dark matter halos that set the gravitational layout and keep systems bound through long interactions. The observational tests match this outline. X-ray maps show hot gas shocked by encounters. Ultraviolet and H-alpha maps highlight recent star formation along tails and in central regions. Infrared observations trace warm dust around young clusters. Radio maps reveal long filaments of neutral hydrogen that connect partners or extend far beyond the bright disks. Lensing maps in clusters place most mass with the galaxies rather than with the slowed gas, pointing to collisionless dark matter. Spectroscopic surveys measure how stars move in remnants and find the increased velocity dispersion expected after major mergers. Each band and method fills in one layer of the same process. For individual stars, the implications remain steady. A merger can change a star's orbit and neighborhood, but not the fusion in its core. A low-mass star will spend billions of years quietly on the main sequence. A solar mass star will end as a white dwarf after a red giant phase. A massive star will explode and leave a neutron star or a stellar black hole. These endpoints help regulate the larger cycle by returning energy and heavy elements to the gas, which in turn affects where the next stars form. The role of dark matter stays central from start to finish. It holds disks together so that spirals can exist. It binds partners so that encounters lead to mergers rather than flybys. It provides the deep wells into which gas flows during starbursts and AGN phases. It also anchors the final remnant, whose long-term stability depends on the shape and depth of the merged halo. The strongest evidence for these statements comes from systems where visible matter and mass maps diverge in collisions, with the bullet cluster as the clearest case. Collisions are a natural way to switch on a quasar. In a single spiral, rotation keeps most gas spread across the disk, and little of it reaches the center. A merger breaks that order. Gravity stirs the orbits, shocks heat the gas, and torques drain angular momentum so material can move inward. With a steady supply of fuel, the central black hole brightens. The accretion disk becomes hot and luminous, and the galaxy that once looked ordinary turns into a powerful source across radio, optical, and X-ray light. Sometimes both black holes in the pair feed at once. Astronomers have imaged dual AGN systems where two active nuclei sit a few thousand light-years apart inside the same disturbed host. As time passes, dynamical friction, the drag from moving through stars and gas, slows the black holes. Their orbits shrink until they form a close pair. That pair keeps tightening. When the separation becomes very small, they will radiate low-frequency gravitational waves and eventually merge. Current ground detectors do not hear these deep tones, but future space detectors are being designed to do so. Before that last step, the inflow of gas can reshape the host. Energy from the active nucleus is not just light. It also leaves as winds and sometimes as fast jets. This energy can heat or expel gas near the center. In some galaxies, that reduces or even shuts down star formation for a time. In others, the push from an outflow or a jet can compress nearby clouds and help form new stars along the edges of the flow. The same central engine can limit or trigger starbirth, depending on gas supply, geometry, and power. This coupling between black hole growth and galaxy growth shows up in a simple trend. Bigger bulges tend to host bigger black holes. Mergers help build both. Gas inflow during an encounter feeds the center. The disturbed motions build or thicken a bulge. Over many events, black hole mass and bulge mass rise together. When two galaxies finally settle into one, their central black holes are on track to coalesce as well, leaving a single, more massive black hole at the heart of the remnant. Timing matters. Long ago, mergers were more common and galaxies held more cold gas. That is why many of the brightest quasars are found at great distances. We see them as they were billions of years in the past, when fuel was plentiful. Their black holes grew fast, reaching billions of solar masses in relatively short cosmic time. Today, disks are more stable and average gas supplies are lower, so strong quasar phases are rarer. Even so, nearby mergers still light up. The antennae pair, about 45 million light-years away, shows intense star formation and disturbed gas flows. Its cores are not as extreme as distant quasars, but continued inflow could raise nuclear activity as the system evolves. On longer horizons, the Milky Way and Andromeda each host a central black hole. Their future merger will likely feed both, raising the central output before the two holes become one. The idea that mergers make galaxies brighter is plain. An accreting black hole can outshine the combined starlight of its host. The broader point is physical, not dramatic. Gravity reorganizes orbits, gas loses angular momentum, fuel reaches the core, and energy comes back out into the surroundings. Most of the time, black holes are quiet because the supply is thin. Collisions change the supply line. When gas arrives, the response is large and the whole galaxy feels it. Galaxies do not evolve in isolation. They live in associations of many members and in larger patterns that stretch across space. Groups hold a few to a few dozen galaxies. Clusters hold hundreds to thousands. On still larger scales, these systems trace long filaments with wide voids between them. Maps from galaxy surveys show this web clearly. Strands of galaxies and dark matter intersect at dense knots, while large empty regions mark places where little matter gathered. The local group, which includes the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and many small dwarfs, is a modest system within a larger region linked to the Virgo cluster. That region is part of Laniakea, a supercluster-scale flow pattern that spans hundreds of millions of light-years. In crowded environments, encounters are expected. In clusters, motions are fast, and the hot intracluster medium fills the space between galaxies. As a galaxy moves through this plasma, ram pressure can strip its own gas, especially from the outskirts. Close passes are common. Full mergers are less frequent than in small groups, but still occur, especially toward the slower, denser centers. The hot medium adds its own physics. Gas can be shocked and slowed, even as the galaxies themselves pass through with little direct damage to their stars. In systems like the Bullet Cluster, the galaxies advance, the hot gas piles up, and the dark matter halos continue largely unaffected. Another view of how different components behave under the same gravitational field. Superclusters are looser. They are patterns in the flow of matter rather than single-bound objects. Over long times, matter streams along filaments toward deeper gravitational wells. Collisions and mergers happen where these flows converge, Groups fall into clusters, and galaxies within those groups interact on the way. Even galaxies that look isolated usually sit on a filament. They feel the pull of neighbors and of the large-scale web, and will eventually meet other systems if enough time passes. The web's origin reaches back to small differences in density in the early universe. Regions with a tiny excess of matter pulled in more material, growing into filaments and clusters. Regions with a slight deficit became voids. The large-scale pattern grew while galaxies formed within it. Collisions are one outcome of this growth because matter gathers into common wells, and the galaxies within those wells move under the same gravity. The mix of quiet and active phases in any region depends on local density, speeds, and gas supply. Seen across these scales, a collision is not an exception. It is one step in an ongoing flow of matter from diffuse structures into dense ones. A group merges into a cluster. Two galaxies in that group pass and merge. Their gas fuels stars and black holes. The remnant settles. Smaller companions are later added around the edges. The web sets the layout. Gravity does the work. Gas and stars show the results in forms we can see. The connection reaches close to home. The Milky Way's outer halo holds streams from smaller galaxies digested long ago. Their stars carry chemical patterns that mark their origins. The elements those stars released became part of the gas that later formed the Sun and the planets. Our place in the galaxy reflects this history. The same basic processes that assemble clusters and filaments also shaped the material that built our world. Groups and clusters highlight another frequent mode of growth, the slow capture of small companions by larger hosts. This process is often called galactic cannibalism, though the physics is simply gravity acting over long times. Dwarf galaxies are common. They contain stars, gas, and dark matter, but their total mass is far below that of a large spiral or elliptical. As dwarfs orbit a massive galaxy, tides stretch them. Stars and gas are stripped in streams that wrap around the host. With each pass, more material is lost until only a core remains or the dwarf is fully dissolved. The universe contains far more dwarfs than giants. Many orbit in the outskirts of big galaxies as satellites bound by the host's halo. Because dwarfs are fragile, their orbits and internal speeds matter. On slow, close, or very eccentric paths, stripping is strong. A large galaxy like the Milky Way pulls stars off a dwarf and adds them to its own halo. Streams mark where the material went, and over time, those streams thin and fade. The process repeats with many different satellites, building up a wide, faint envelope of stars around the main disk or bulge. Gas in dwarfs can be removed even faster than stars, especially in groups and clusters where hot plasma and ram pressure assist the tides. Once gas is stripped, the small system cannot easily form new stars. What remains is a dimmer, more diffuse object or a set of streams that trace the last orbits. This steady feeding is not rare. Most large galaxies show signs of past captures in deep images. Shells, ripples, and arcs at very low surface brightness, kinematic substructures, and mismatched populations of stars at large radii. In a statistical sense, this quiet mode of growth is common. It runs in parallel with the rarer, dramatic major mergers. The big events reshape the inner structure, build bulges, and feed central black holes. The small events thicken disks, build halos, and leave long-lived traces in the outskirts. Together, they produce the galaxies we see today, with inner regions that reflect a few large encounters and outer regions that store the record of many small ones. Far from being rare, this process has shaped nearly every large galaxy in the universe. The Milky Way, is a clear case of a galaxy that grows by eating smaller neighbors. In its faint outer halo lie long, ghostly trails of stars that do not match the ordered paths of the spiral arms. These are tidal streams, the stretched remains of dwarf galaxies drawn out by gravity. They show that our galaxy has added to its mass, not only by forming stars quietly in its disk, but also by taking in companions over long spans of time. One of the best examples is the slow breakup of the Sagittarius dwarf spheroidal galaxy, found in the 1990 seconds. This small satellite is being pulled apart by the Milky Way's gravity. Once a compact companion on an elongated path, Sagittarius is now a ribbon of stars that wraps around the sky in great arcs. Each time it passes through the Milky Way's disk and inner halo, tides strip more material, leaving bright strands that circle the galaxy. In the end, Sagittarius will be fully mixed into the halo, its stars moving as if they had always belonged there. For the stars inside a dwarf galaxy, this process is quiet. Stars almost never collide. Instead, their orbits are slowly reshaped. A star feels a gentle pull over millions of years and finds itself on a new path, part of a widening stream. From a planet bound to such a star, the changes would unfold far beyond any single lifetime. Patterns in the night sky would drift so slowly that only careful records across many generations would show the difference. Sagittarius is not alone. The Milky Way hosts many satellites, including the Large and Small Magellanic Clouds, two irregular galaxies visible in the southern sky. They are interacting with each other and with our galaxy. Gas pulled from them forms the Magellanic Stream, a long trail that traces their motion and the Milky Way's pull. Over long times, modeling suggests that even the Large Magellanic Cloud may spiral inward and be absorbed, adding its stars and gas to our system. This steady feeding is common. Giant ellipticals at the centers of clusters show halos filled with faint arcs and shells, records of many past meals. Their smooth, bright bodies and broad envelopes tell of repeated accretion and mergers. Andromeda, our nearest large neighbor, also carries a patchwork of tidal streams in its outskirts, evidence that it too has grown by taking in sizable dwarfs. When Andromeda meets the Milky Way in the far future, the remnant will inherit both histories and the debris of many swallowed companions. The driver is gravity. Large galaxies sit in massive dark matter halos that extend far beyond the visible disk. These halos make deep wells. A small galaxy that wanders close can become bound and lose energy through repeated tides and encounters. Its orbit shrinks. On each pass, some stars and gas are peeled away and left along the path. After billions of years, little remains of the original core. The stripped stars add to the larger galaxy's halo. The gas, if not removed by the hot medium, can cool and join the disk or inner regions. For astronomers, these streams are valuable records. By mapping their positions, motions, and chemical makeup, researchers reconstruct which systems were accreted and when. Different dwarfs form stars under different conditions, so their stars carry distinct patterns of elements. Those chemical fingerprints help sort the streams and trace the route of each past merger. The shape of a stream also responds to the overall gravity field, letting scientists test the form of the Milky Way's dark matter halo. Despite the dramatic name, galactic cannibalism is a slow, ordered process. It adds variety to a galaxy's stars and enriches the gas with heavier elements from many sites of star formation. The Milky Way's present look, its thickened disk, its globular clusters, Its layered halo reflects this long diet. Even the material that formed the Sun likely includes atoms forged in stars that belonged to now vanished dwarfs. The picture is not one of sudden ruin, but of gradual blending. Gravity stretches a small galaxy into threads that thin and fade until they are part of the larger whole. It helps to keep a sense of scale. If the universe were a banquet, dwarfs would be the appetizers and major mergers the main course. Sagittarius is a snack that has lasted for billions of years. The future union with Andromeda will be a far larger meal that reshapes the core structure. Between such extremes, the Milky Way continues to collect small companions, adding stars to its outskirts and keeping a record of the process in low surface brightness arcs. What emerges from this steady intake is not waste, but transformation. The smaller system loses its shape, but its stars keep shining inside a new home. The larger galaxy gains mass, diversity, and extended structure. Over and over, small stories are folded into a larger narrative. The practice is widespread because gravity is universal and dark halos are broad. Wherever a large halo overlaps the path of a small one, tides begin their work. The future of our neighborhood follows the same rules. The Milky Way and Andromeda will merge into a single, more massive system often nicknamed Milkdromeda. After that union settles into a rounder, thicker form, the remnant will continue to pull in surviving satellites from the local group. The Triangulum Galaxy may join, and many faint dwarfs will be stripped and added as streams. A scattered collection spread across a few million light-years will condense into one dominant galaxy with a wide halo built from many sources. Across the universe, similar outcomes are expected. Groups drift inward along filaments and fall into clusters. Within groups, large members absorb small ones. Inside clusters, repeated encounters in the hot intracluster medium help remove gas and add stars to central giants. The broad pattern is consolidation. Fewer systems with more mass, assembled from many parts over long times. Dark matter sets the pace. Halos overlap long before the bright disks touch. Once two halos link, galaxies become bound. Loss of orbital energy is slow, but relentless over billions of years. The end state, in many regions, is a landscape of very large, smooth ellipticals, each the product of many mergers and countless accreted dwarfs. Spiral structure becomes less common as gas is used, heated or stripped. The mix shifts toward older stars and rounder shapes. As the universe ages, the number of such events declines, but the ones that occur can be more decisive. Distances between major galaxies grow in expanding space, yet in bound regions their relative separations and speeds still favor encounters. On the timescale of billions of years, the result is clear enough to track. Galaxies are close compared with their sizes, and the combination of gravity and broad halos makes collisions common across those spans. Cosmic expansion changes the picture. Space itself is stretching, driven by what astronomers call dark energy, so distant galaxies are carried away by the expansion rather than by their own motion through space. Over very long times, only systems held together by gravity, like the galaxies in our local group, will remain near enough to interact. Everything else will drift beyond our cosmic horizon, receding so fast with the expansion that their light can never reach us again. In that future, Milkdromeda and the few companions that fall into it are a rare final act. Beyond our neighborhood, the wider universe will slip out of view. Imagine a night sky seen by a civilization living trillions of years from now. Long after the Milky Way and Andromeda have settled into one galaxy, the sky would look much emptier than it does today. Their instruments would find only their own vast system. The spirals and dwarfs we see now with telescopes would have faded beyond detection, not because they vanished, but because space has stretched the distance between us and carried their light away. This casts the future of collisions as both grand and quiet. The merger of the Milky Way and Andromeda will be a major transformation for our region. Yet, it will unfold while the broader stage dims. Groups like ours will become isolated islands in a deepening dark. Within those islands, starbirth will continue for a while. Mergers will drive gas inward, starbursts will flare, and some nuclei will shine as active galaxies and quasars. But gas is limited. Star formation consumes it, and outflows from supernovae and black holes can eject it. Over time, the supply thins. Star birth slows and then stops. The large ellipticals left by mergers will age into calmer systems. The bright, short-lived stars will be gone first. Long after, only small red dwarfs will remain, shining with low light for trillions of years. Galaxies will take on a faint, reddish glow. Collisions will still occur, but with little gas left, they will mix old stars rather than spark new ones. Farther ahead, even red dwarfs will exhaust their fuel. What remains are stellar remnants, white dwarfs, neutron stars, and black holes moving through a quiet halo. On timescales beyond easy comprehension, even black holes are not fully permanent. Theory predicts that they very slowly lose mass by Hawking radiation, emitting tiny amounts of energy over unimaginable spans. If that process holds, the most massive black holes will also fade, leaving a trace of energy in an otherwise thin, cold universe. In this view, collisions are more than one stage of history. They help set up the last structures that persist as the lights dim. There is a calm lesson here. The universe is not rushing toward a sudden end. It changes steadily. One merger, one star, one gas cloud at a time. The pace measured in billions and trillions of years. Great collisions will be among the last bright events before the long quiet. Their marks will remain in the shapes of the galaxies they built, the stars they ignited, and the heavy elements they spread. Collisions also explain much of what we see today. Two galaxies begin to feel each other long before their disks touch, because their dark matter halos overlap. That gravitational handshake pulls and stretches them. Bridges and tails of stars and dust trace the changing gravity field. Gas clouds are compressed. New stars turn on. Nuclei can awaken and feed. Without these encounters, the universe would host fewer stars, fewer planets, and fewer chances for life. The most common galactic forms, spirals, built by cooled rotating gas, and ellipticals built by violent mixing, arose through these processes. By watching collisions at different stages, astronomers learn how disks become spheroids, why some systems grow quiet, while others flare as quasars, and how dark matter shapes the visible parts. Each merger is a natural experiment that runs under the same basic rules, with results written in starlight and motions we can measure. The images made by modern observatories show the evidence clearly. Arms twisted into arcs, knots of newborn stars along tidal streams, bright cores where gas has reached the center. What looks like chaos is regular physics, acting over long time. The scale of patience in these events is easy to miss. A major merger lasts hundreds of millions to billions of years. If you could watch in real time, a collision would feel slower than seasons, slower than continents drifting. Stars would keep their steady fusions going, barely noticing the change in their orbits from one lifetime to the next. Seen in short snapshots, these encounters appear sharp and dramatic. Seen across their full span, they are measured and deliberate. It helps to hold two views at once. Up close, a collision is all detail. Clouds compressed, clusters formed, jets and winds launched, tails curving through the halo. Far away, it is a single movement. Two patterns of stars shifting into one, then settling. Both views are true. Both reveal a universe where change builds structure rather than erasing it. A galaxy can be stretched and folded, yet its stars continue on paths set by gravity. Gas can be heated and blown out, yet some will cool again and, given time, form new suns. Our own galaxy is part of this long rhythm. The Milky Way carries streams from past meals in its halo. It is moving toward Andromeda under the pull of their combined halos. After they meet and settle, the remnant will keep collecting smaller companions from the local group. The broad trend elsewhere is similar. Matter flows along filaments. Groups merge into clusters. Central galaxies grow. Outskirts fill with faint debris. Meanwhile, the expansion of space separates these islands from one another more and more. In that far future, observers inside a bound remnant may not know the wider web ever existed unless they recover clues from their own galaxy's fossil record. The picture would be a single, dominant system surrounded by a sparse halo. No background of distant galaxies, no cosmic web in the sky. Only careful physics and ancient archives of light would hint that the universe was once packed with bright islands strung along filaments. On human scales, these spans are beyond planning or worry. The Milky Way-Andromeda merger lies billions of years ahead, far past the Sun's present phase. There is no practical concern to carry. The value is in the perspective it gives. Collisions show that the cosmos is not fragile. It changes form and keeps going. Stars rarely strike each other. Planetary systems usually stay bound to their stars. The grand motions are slow enough that life, when and where it appears, can unfold while galaxies rearrange in the background. So the subject closes where it began, with gravity, dark matter, gas, and time working together. Collisions do not just break things, they organize them. They give galaxies their shapes, set the pace of star birth, and outline the hidden halos that hold everything together. They create sights that are both informative and quietly beautiful arcs of light, rivers of stars, cores warmed by infalling gas. And they tie the past to the far future, linking the busy, spiral-rich universe of today to the calmer, redder universe to come. If you step back in your mind and let the timeline stretch, the pattern is steady. Two galaxies approach, their halos meet, tails unfurl, stars ignite, a remnant forms, the lights slowly soften, the island drifts in an expanding sea. The details change from case to case, but the rhythm stays. In that rhythm, there is order, and in that order, there is a kind of reassurance. Even as the sky grows quieter in the deep future, the work of these collisions will still be present in the forms that remain, in the elements within old stars, and in the long, faint paths of light that once traced the meeting of worlds fading, but still there, like the last glow after sunset, lingering at the edge of night.